Yeah, that works perfectly. So just as a little bit of an introduction, just one sentence. Yeah, today Artemi, who has also some works on Turing machines and like really bright work, recent work on Turing machines, he's going to talk about, in general, stochastic thermodynamics with the flavor of algorithmic information theory. So Artemi, it's yours.
Thank you so much. Thank you to the organizers. I'm really enjoying this workshop. It's really one of my favorite workshops I think I've ever been to. Thank you, Gulce, for emergency chairing. And I'm very honored to be here and to talk to you. And so today I'll be talking about the algorithmic cost of a single classical or quantum computation. David set me up perfectly because I'll be working in an inclusive Hamiltonian formalism. And the archive for this will appear shortly, I hope in the next week or two. But please, if you have questions or you want to get, the preprint when it's ready, please just email me. My email is right there. Let me begin by discussing what I mean by the cost of a single computation. So let's imagine, a situation where we have some kind of physically instantiated computer, and it's coupled to a heat bath, and it's getting inputs X, and it's emitting outputs Y. And we want to study the fundamental thermodynamic costs of this process. Well, the most famous result in the field is, of course, Landauer's bound. And Landauer's bound tells us that any decrease in the statistical entropy of the logical states of the computer has to be compensated by generated heat. And here Q, the expectation of Q, is the expectation across computational ensembles, and S is the Shannon entropy. And I'll always here be working in units of bits, and I'll write heat, I'll set beta to log 2 just for simplicity. So here we see that across this ensemble of inputs and outputs, the cost is given by the loss of statistical information in the statistical ensemble. But there's something kind of weird about that, because it's actually not really what we might care about. What we might care about is what is the cost of putting in 2 plus 2 and getting 4 out, or of cracking some encryption scheme. We don't really want to say what ensemble those inputs came from, because that actually reflects something about maybe our uncertainty or our subjective expectation about the computer rather than the actual physical process that's running. And can we think of a thermodynamic cost of a single computation that maps a single input to a single output? And can we define some kind of cost that's defined in terms of the properties of those inputs and outputs, right? And I think this is actually closer to what we might actually care about. And just an analogy, by looking at the Landauer's bound, we might think that maybe this could be done if we had some kind of theory of information at the single instance level. So something about the loss of single instance information could be used to quantify this cost. Well, it turns out that there is such a theory. It's called algorithmic information theory. And I'm going to introduce it now by comparing it to the known and beloved Shannon information theory that we use all the time. So Shannon information theory is an ensemble-based theory of information. The core quantity is Shannon information, or Shannon entropy. It's also the core quantity in non-equilibrium thermodynamics. And the information in statistical ensemble is defined as the uncertainty about the outcome. So if we have a very peaked ensemble, then we kind of know the outcome is going to be 1. If we have a very uniform looking ensemble, then we have high uncertainty, high information, high entropy. Let's compare this to algorithmic information theory, which is an instance-based theory of information. And here, information in, let's say, a binary string, but it can also be defined for other objects, is defined as the minimum description length of that string. Okay, and what do we mean by minimum description length? What is the language? Well, the language is going to be defined by a universal Turing machine, or also known as a universal computer. And we're going to define this quantity, which is the core quantity in algorithmic information theory, called Kolmogorov complexity. And so the Kolmogorov complexity of a binary string relative to some universal computer M is the length of the shortest program for M. When plugged into M, it gives us that string. Okay, and This actually behaves very similarly to Shannon information or Shannon entropy, but is defined at the level of instances. And we can also generalize this to define the conditional Kolmogorov complexity, which is kind of like conditional entropy. And the conditional Kolmogorov complexity of x given y is just the length of the shortest program that outputs x when y is provided as another input. Now, to give you a little bit of intuition, some of you are familiar with, for those not, a picture of a fractal has low algorithmic information because there's a very short computer program to generate it. And a picture of random noise, truly random noise, would have very high algorithmic information because there's no compression, there's no compressed description of it. Great, so before proceeding, I'll just mention two important things about Kolmogorov complexity. One, it doesn't really depend on the choice of the universal computer because computers can translate their languages between each other. So there's going to be a constant that doesn't depend on x that has to be taken into account if we want to move from one computer to another computer. But this constant kind of goes away for high complexity x. And the other thing is, some of you might know, the Kolmogorov complexity is actually uncomputable. Well, we can get better and better upper bounds on it. So it's what's called upper semi-computable. And I won't delve into this, but this is something to keep in mind. We could discuss in question time if you're interested. But the point is, we can bound it arbitrarily well. Now, the question is, can we use algorithmic information theory to study the cost of a single computation, where a single input is mapped to a single output? And it turns out this question was actually considered before, and a proposal was made in this very interesting paper by Zurichs. And it was published in actually Nature in the late 80s. And Zurichs considered the following setup. There's a classical system that takes as an input some string x and outputs some string y, and it's coupled to some kind of equilibrium environment. And what Zurichs proposed is that in carrying out this computation by a physical process, there's a fundamental bound on the generated heat. Now, notice we're not averaging the heat across the ensemble. We're saying the heat just produced in that single instance is bounded by the conditional Kolmogorov complexity of x given y. And I should point out a few things. First, this is a classical system, and it's a deterministic computation, so y is always produced. The other thing is, so here, this is the conditional Kolmogorov complexity, this is the heat, this is an additive constant, and this additive constant can depend on the choice of the universal computer used to define the Kolmogorov complexity, but it can also depend, and this is not, I think, not really appreciated at the time or for a while, it can also depend on the choice of physical process used to run the computation, meaning for a given xy, we can design a very special process that makes this bound kind of trivial. But for a given process, for a fixed process at any epsilon, what this basically means is that we can choose some very complex x such that the heat generated really, it can't be much different than the Kolmogorov complexity, the conditional Kolmogorov complexity. And we can also compare this to what Landauer's bound looks like for deterministic computation. And for deterministic computation, it's actually given by the conditional entropy of the input given the output, just like the algorithmic version. So we can kind of think of Zurichs bound as representing a loss of algorithmic information in the computation. Now, there's a few serious issues with Zurichs' result, unfortunately, and I'll summarize just a few of them. So maybe the most serious one is that the derivation is highly informal, to say the least. And I think if you read it from the point of view modern non-equilibrium thermodynamics, remember this was in the 80s, this was far before stochastic thermodynamics, it's kind of hard to make sense of it. And maybe there's even some quite questionable steps. And one of the questionable steps is that actually in deriving the bound, it invokes Landauer's bound, which was known at the time. But of course, Landauer's bound is essentially an ensemble-based result. It only has to do with statistical ensembles. So the fact that the derivation used Landauer's bound strongly suggests that there's some kind of implicit assumption of an ensemble. It's also, limited to classical and deterministic computations, and this constant has an arbitrary dependence on the choice of physical process. As I mentioned, I'll show you what that means. Basically, it means we can design special processes that make the bound trivial. And before proceeding, I should add that some of these issues were discussed in this review paper about stochastic thermodynamics of computation by David, who also formalized some of the steps of Zurichs' approach and discussed them. And that in my paper with David on the thermodynamic cost of Turing machines, we actually derived the same bound, I would say, in a more rigorous manner using a very different approach. But it was still limited to classical noise-free computations. And it was also, based on some idealized assumptions like coupling to an idealized heat bath and so on. And so, kind of inspired by some of the ideas that arose when working on this paper that appeared in Physical Research, I started thinking about, that there seems to be actually a very deep relationship between Zurichs bound, the general idea of a thermodynamic cost for a single computation, and stochastic thermodynamics as we now understand it, as a theory of thermodynamics for individual trajectories. And so my goal here is to use ideas from stochastic thermodynamics to derive a generalized version of Zurichs bound. And I'm going to derive it rigorously within an inclusive Hamiltonian framework. Our derivation will generalize immediately to classical and quantum noisy and deterministic processes, and will explicitly account for the choice of physical process, and in particular what I will call the complexity encoded into the process. Great, so let me proceed to part 2, which is basically the result and associated things. So I'll talk about the physical setup I consider, the main result. I'll discuss a resource trade-off that is implied by the main result, and I'll provide some examples. And I'll go over the derivation, and I'll briefly touch upon the achievability of the bound. So the setup, I think, will be quite familiar to many of you. We have some input state X. So we can think of this as, for example, a vector from a basis of logical states. It gets fed into a computer, which can be classical or quantum, which is coupled to a heat bath, and it spits out output states, which let's say are also vectors in this logical state basis, with some probability distribution Py given X, okay? Or a little bit more formally, we start with a separable pure state. This is the input state. This is a state of the bath, which is going to be sampled from a Gibbs ensemble. And this then undergoes Hamiltonian evolution, giving rise to this unitary over the system and the bath. And after that evolution, we perform a projective measurement. We measure the state of the bath, and we measure the output state of the system. And this gives us actually a conditional probability distribution of observing output y alpha prime. Alpha prime is the output state of the bath, final state of the bath, given the initial conditions. It's given by Born rule. Okay, and so some of you will recognize this is basically a 2-point measurement scheme that's used frequently in quantum thermodynamics. It's quite standard. The general result, I'll talk about it, can be actually generalized. It can be generalized to things like, when the logical states are coarse-grained macro states, or when the measurement of the output is done on a different basis than the input, and so on. So given this setup, we can define now what we call the noise, which is just the stochasticity in this computation. And that's done by averaging across the states of the initial states of the bath drawn from the Gibbs ensemble. And we can also define the heat in this computation. So it's going to be the energy dumped to the bath averaged over instantiations here. And we're going to make the following assumption, which is, I think, somewhat unusual to many of you, but which is kind of one of the core ideas here, we're going to assume that the physical process, and by physical process, what I mean is the unitary that's implemented, the evolution, and the ensemble of the environment, the bath ensemble pi. We're going to assume that these two objects are computable, meaning there's some computer program that can, let's say, spit out their coefficients to any precision we would like. And physicists, I think often, and for Zurichs surely did just this, he didn't even, I think, think about this. He just assumed it was computable. Physicists often assume everything can be, this is kind of a funny assumption, right? It's weird to think of a physical process that cannot be simulated on a computer. Now, mathematically, such things exist. Whether they're physically relevant touches upon a philosophical issue, which is called the physical church Turing thesis. And it's there's a lot of interesting connections that maybe I can touch upon in the question time, but I won't get into. But we're just going to assume we can calculate this unitary, we can calculate the distribution by a computer program. So given just this assumption and this very general setup, we now have the result, which is a generalization of Zurich's bound that's derived in full rigor. And this bound says that there's this fundamental algorithmic cost of computing output y from input x. And it is the conditional Kolmogorov complexity of the input given the output. It's the loss of algorithmic information, okay? And this bounds the sum of three resources, we could think of them. So the first resource is the heat expelled to the bath. This is the thermodynamic cost. The second resource is the non-determinism, or the noise of the computation. And the last resource, which will be the most unfamiliar, I call the hard-coded complexity. So this is something called the algorithmic mutual information between the process and the input conditioned on the output. And the algorithmic mutual information is defined exactly as mutual information is defined in Shannon's theory. It's basically the conditional information, the information without something and the information when something else is provided. So here, when we provide the unitary and the bath ensemble, how much does the complexity of the input decrease? And typically, this is going to be a sub-extensive term, though not necessarily, and it can always be bounded by just the description length of the computer program that computes our physical process, that can basically simulate our physical process, okay? I'm gonna, this bound sets up a trade-off between these three resources, which I'll illustrate with an example in the next slide. So I also want to point out that the non-determinism, the noise, can actually, this last term is an additive constant, which now doesn't depend on the choice of physical process, but just on the choice of the Turing machine used to define the Kolmogorov complexity. And the noise can also be decomposed into three contributions, which can be either classical or quantum. So there's a contribution from the bath and the system becoming entangled. There's a contribution between the system becoming coherent in the logical state basis. And those are both quantum, of course. And then there's the contribution from the randomness in the bath. And that's the classical contribution. Okay. So let me discuss this, I think, quite interesting trade-off between what I call these three resources: the heat, the noise, and the complexity. I'm going to illustrate it with an example, and the example is quite, I think, simple. We have a huge hard drive, let's say 100 gigabyte hard drive, and it starts in some very long and incompressible binary string, which is, all our Dropbox or whatever, and we want to erase it, and we want to map it to an all-zero string. What can we say about this single instance computation, which we map this single initial state to the single final state? Well, the bound tells us that there's actually this kind of space of physical processes, and there's a physical region, feasible region, defined by the sum of these resources, the noise, the heat, and the hard-coded complexity, that can't be suppressed. But we can imagine, different strategies for saturating the bound. And I'm going to illustrate the three corners of the feasible region. So the first corner is high heat. And this is just, let's say, Landau erasure. We map all initial states to the final all zero state. And we know we have to generate a lot of heat. Even on that single instance, it can be shown that we have to generate a lot of heat on every instance, basically, that's the heat corner. Now let's think about the noise corner. So the noise corner could just be relaxation, free relaxation to a uniform equilibrium. No heat has to be generated. There is some probability that we'll reach the final 0000 state, but of course that probability is going to be really tiny. And yet another strategy for high noise and low heat, low complexity is that the system and bath go to a maximally entangled state. And so then when we make the measurement, we get this very high entropy output. And again, there's a very low but existent probability that the hard drive gets erased.
Hi, Timmy. You were just
finally, let's think about.
Sorry, I have to say that
Thank you.
This is the question time. Okay.
So, and the final corner is given by the high complexity regime, which is basically we can create an invertible map, which just swaps the random binary string and the all zeros vector, right? And leaves everything else the same. This doesn't have to generate any heat. It can perform the erasure reversibly, but it has to hard code in the entire 100 gigabyte state of the hard drive basically into the Hamiltonians or into the unitary. And so it's just kind of, it just hides away the complexity somewhere else. Given the time, I won't go over the derivation of the result. I'll just say that it has to do with a very weak form of micro-reversibility, which is used when deriving quantum detail fluctuation theorems and generally Hamiltonian detail fluctuation theorems. I'll just say one thing, which is we can think of the result as a kind of algorithmic detail fluctuation theorem. It actually doesn't use it doesn't explicitly use any notion of a reversed process as usually appear in detail fluctuation theorems. What it uses is the fact that we can use a computer program to somehow invert the stochastic transition matrix that arises from our protocol. So it's kind of like the reverse protocol is now played by the part of a computer program computing a reverse probability distribution. And then the final thing I'll say is that we also have an achievability result. We can show that, given some kind of map that we want to carry out and some kind of level of complexity, we can actually achieve, at least in principle, using a highly idealized protocol, we can achieve the heat bound. So it is possible to achieve it. So thank you very much. And like I said, the archive will appear soon, and I look forward to answering your questions. Thank you.